All right, class. So in this webinar, we're going to cover some of the analyses tools that you're going to use to help you work up and analyze your benchtop performance data, your biocompatibility in vitro tests, and your chemical characterization tests. So the first thing we're going to get into are the standards curves that are pretty ubiquitous in all of your chemical characterization methods. So your different chromatography methods, ICP, and whatnot. So I know we talked a little bit about this in our chemical characterization testing, but a standards curve is basically made up of known concentrations of your analytical standards, where you typically start off with maybe one analytical standard that you got from a vendor that has a calibrated and verified concentration. Then you undergo serial dilution in order to get lower and lower concentrations. As long as you keep track of the diluent amounts, you have a standard set of now known concentrations from which you can run an analytical method and get some sort of response. So the whole purpose of this is generate a graph like the one you have on the right-hand side, where you have known concentrations and you get a known response on the y-axis from your analytical instrument, and you can generate a y equals mx plus b, a linear regression line. Now, it doesn't have to be a linear regression. It could be a sigmoidal. Different assays have different trends. But in these particular tests that I gave you, you're going to have linear trends in these. So that simplifies it a bit. Now that you have your standards curve, you're going to go back to your test samples where you have unknown concentrations of some sort of analyte, and you want to run those on your analytical instrument method in order to determine, hey, what's the actual concentration of something coming out? So in this case, you'll get a known response from those samples, and you want to back calculate, okay, well, how does that response correlate to the concentration? So that's your objective, to find out what concentration is coming out of. You see where the response lines up on your curve, and then you go to see where it intersects on that particular line in order to find that concentration. Now, within your standards curve, you also include standard blanks. So these are ones that aren't subjected to the test condition. They're not undergoing these extractions or leachables testings. So therefore, it's not typical that they get included within standards curves, but they are important in that they provide background noise of the standard and instrument, but not the test sample. So we'll get into those differences later. So if you notice here on the right, in comparison to the previous test, now we have that x equals 0 data point in the bottom left-hand corner. And that's what's going to help in part understand where that y-intercept is. Now, you could exclude that and you could still get a y-intercept. And I'll talk about how you actually include that in your data analysis. There's a few different schools of thought on that. But if there's cases where if you have more noise, that's simply going to raise that background level. So again, kind of going back and forth, no matter what, the amount of background noise is simply going to raise that and shouldn't interfere with your actual slope. Now, we just talked about your standard blanks. You're also going to have sample blanks that don't include your test article, aka your implant, but these vessels and the extraction media are going to be subjected to the same test conditions as your implant extraction test, meaning you're going to have that same matrix, methanol, acetone, toluene, water, whatever, in the glass or the vials, that the same ones that your test implant has. They're going to be heated to the appropriate temperature. They're going to be subjected to the same amount of times of the extractions. Basically, any way to understand what are the impurities throughout this test process, what leaches from the glassware or the plasticware that you're doing these in. They're going to be subjected to the same sampling conditions, atmospheric conditions. So they're intended to provide background noise of absolutely everything, not only the instrument, which the standard blanks have, but everything within the test sample process. Now, this is the data that you've been provided. It could be considered a robust method to actually have your standards undergo the same exact conditions. And oftentimes this is done, or maybe even mandated, not in chemical characterization, but if you're doing a blood assay, you need to spike your analytical samples in blood or plasma matrix in order to understand how those background effects somehow interfere or confound your particular analytical standards. So that's more of a side note. That's not representative of the data that was given. But in this case, it's important to understand how these two are different because you need to be mindful how to apply and keep independent these two respective calibration or various types of blanks. Now, I pulled a slide from our chemical characterization tests that talked about the uh, AET and the different analytical thresholds that your chemical characterization, your analytical instrumentation needs to maintain. We talked about the limit of detection, limit of quantification. So I just want to revisit some of those definitions and also go about how you're going to try to obtain these. Now, there's various definitions on what a signal to noise ratio is, what constitutes noise, what constitutes signal. I think conceptually we can understand what that means, but there's actually an FDA guidance document that's applicable more to analytical techniques within the CDER, meaning the drug division or the biologics division, but they do provide some guidance on how to interpret some of these. And for the methods that we're going to choose, we're actually going to slightly alter our definition for the limit of detection, which is a signal to noise of 3.3 to 1, as opposed to a 10 to 1 for the limit of quantification, which holds true for both definitions that I've referred to. So in order to get that, we can actually understand the noise and learn how to apply those with our both standard blanks and our test blanks. So here's kind of the order of how you're going to do this. For the standard blanks, instead of including them in your calibration curve, meaning you don't necessarily want that y equals mx plus b line, that y-intercept is less important to you. You want to subtract the average of those blanks from all of your standards results. Okay, so I should have modified not from your test results, but only from your standards results. This is in effect getting rid of that background noise from all your samples and should in effect just move that line down and not affect the slope. So you should get a value whose y-intercept does approach 0. And maybe if you had slightly different bias results at the higher concentrations, it might not technically be 0, but it should be pretty close. And it should still preserve that original slope. Now, you're not going to apply that subtraction to your test blanks, okay? So I want to stress, you don't want to mix these two up. This only applies to your standards and your standard blanks. Now, for your test blanks, you do want to average all of the results of your test blanks and subtract them from all your test samples. This is, in effect, getting rid of the noise from all of your samples. Then you want to apply the calibration curves using just the slope because you're not interested in that y-intercept, but you're going to use basically a y equals mx calibration curve or a standards curve in order to go from your analytical result, absorbance values, CPS values for your ICP, and turn that into a quantitative concentration. And then, in order to determine that important noise factor for your LOD or your LOQ calculations, that's where you're going to take the standard deviation of the test blanks and then apply that into these equations that we had before. So sigma is your standard deviations, and then S is the slope of your y equals mx line. So again, even though we had that y equals mx plus b, that b isn't going to really help you in any of your calculations. I recommend subtracting the background noise from the two respective groups and only using the S for your calibration curve and for your LOD and your LOQ calculations. Right, so I can't highlight that, keeping those two independent enough. Now, some good regression, good practices is you don't want to forecast values, meaning you want your highest calibration point to extend beyond your test sample data set, and you want your lowest calibration standard to be lower than any sample. Okay, now your highest calibration standard, You could, in theory, go many orders of magnitude depending on the sensitivity or the upper limit of your analytical instrument, but you don't want to go so many orders of magnitude above, like maybe more than one order of magnitude, because the higher concentration samples can bias and affect your regression line beyond a means that's practically applicable to your data set. Okay. Who cares if your standards curve can go up to, a kilogram per milliliter or some ridiculous amount? If all of your sample concentrations are in the order of milligram or microgram, you don't want those higher data points skewing the regression curve to favor the higher concentrations where none of your data is. Now, for the lowest calibration, FDA doesn't really care if your lowest value is below your lowest calibration center is below the value, because in effect, the limit of detection and the limit of quantification is a much more robust way of saying what your true lower limit of quantification is. Now, you do want to check for linearity, meaning it's very possible that some of your analytical instruments kind of get skewed at the upper limits. You oversaturate and you start getting a linear response with increasing concentrations. If that's so, you want to check for saturation and eliminate any standards that you can argue or justify go beyond that linear range. And you can do that easily by checking the R squared value and saying, hey, I'm not seeing a trend upwards anymore. If I eliminate those top samples, it clearly improves the linearity of my line. Now, I say that with a few caveats in that you don't want to get in the practice of just fixing R squared values. And by that, I mean, hey, data's data. And if you have a bad regression line that's kind of within your test sample range, that speaks more towards the quality of your instrumentation, less so the linearity of the standards range that you chose. So beyond just checking for saturation, even if you have a poor regression analysis, you got to keep it. And any data that you do choose to eliminate, you do have to justify. So always consider that when you're trying to change values in order to game or fix that R squared value. And also understand the limits, right? Data below any kind of noise has to be interpreted as zero. Now, that should usually be a good thing, right? If you're trying to detect for possible carcinogens and you do find some values, but they're below your LOQ, great, interpret it as zero, and then you don't have to report it, okay? As long as you can justify that, that's a good thing for you. So, a few tools to help you understand this. I think it's pretty intuitive. Most people understand, hey, if I put this data on a graph, I can right click and say add regression line, and it'll spit out a y equals mx plus b line. It'll spit out a regression line. But there's some better formulas within Excel to help you do that, because I think if you do have that pasted equation, the graph, then you have to sort of hand write that slope, that intercept value into another cell in order to use it for later calculations. It's not formatted properly. Better to just simply plot a slope or have a formula that can output the slope, the intercept, the R squared value. So I put those formulas here. They're pretty intuitive. The slope equation is equals slope. And then you just format, you highlight all your Y values for your concentrations. Remember, don't include the blanks in here, along with the corresponding known X's. You do the same thing for intercept, and your coefficient of determination, aka the R squared, is RSQ. And again, known Y's, known X's. I talked about averaging blanks. I talked about picking the standard deviation of blanks for your signal to noise ratio. So average is pretty easy. You just pick all the values within there and use the average formula. stdev.s technically stands for the sample standard deviation. There's also a population, the .p, but that's only if you know the true core data set. Hey, I tested every person literally in America, and here's their average height. If you're only using a small subset, you do the sampling as opposed to the entire population, so the .s. Now, I mentioned you want to interpret every value below your LOQ as zero. So I oftentimes use if or logic formulas where If a particular value is below my LOQ, have it output as 0, and if not, if it truly is above my LOQ, then have it output the result of my regression analysis. So you might use a logic formula like the one I have here, put in a formula like, oh, cell C2, which is the value I'm analyzing. If it's less than my cell that has my calculated LOQ, okay, then make it 0. If it's equal to or greater, then, make it equal to whatever the output of your regression analysis is. So that kind of takes us through our chemical characterization analyses. Next up, I think perhaps a bit more relevant for your column analyses is your performance tests, where you have data sets of various cyclic fatigue samples. You have your biocompatibility tests where it's just here's the end of the result. I want to compare one group with another, one column with another. And that goes into various statistical tests to determine which ones are different from one another. Is one significantly greater, or some amount of values greater than 20%, or whatever your acceptance criteria are? So, some common questions is within a particular column analysis, where maybe like the graph on the left, you have some sort of output, at baseline, you're comparing it to the test after 5 million cycles of a fatigue test. You might want to ask, is there any difference between these two groups? Now, in the sample I'm showing you here in the example, there are only two groups, in which case a student's t-test, which I think is a very default test. I think a lot of undergraduates and graduate students are familiar with student t-tests, is a great option. And it's used specifically to compare the means of two groups and see if they're significantly different from one another. You can also ask if you do a one-way test, if one is significantly greater or specifically less than another test as well. So you only use this when you only have two groups. The data is normally distributed, in which case all this is in the sample sets I gave you. And the variable is continuous, meaning whatever my output is, deflection, absorbance reading, is on a continuous spectrum, as opposed to discrete, like output of a survey, yes or no, or a scale of 1 to 10, 0, 1, 2. Those are discrete steps and not continuous. Now, you could do this in an unpaired, a paired, or a one sample t-test. So pairing has to do with whether or not the samples before and ever, maybe like in this case at 0 and 5 million cycles, if the individual data points represented between those two, if they represent independent samples, or if these are the same samples tested at one time point and another time point. So unpaired would mean that they're totally independent, right? Here's my placebo group, here's my treatment group. A paired test is when they are the same. And it's like, hey, here are my samples at baseline. Here they are after some amount of time, some amount of treatment, and so on. So you want to make sure you pick the correct one. And a lot of these tests are your performance tests. I think they're going to be paired. In some of your in vitro biocompatibility tests, they should be unpaired. And then a one sample t-test is when you're not comparing between two groups, but you're comparing if one group is equal to like a product specification. Hey, is this group equal to zero point 0.3? It has to be larger than 0.3, or so on. So now I'm going to show you how I set some of these up within Prism by GraphPad. And I sent you earlier in the semester an invitation to join those. It's a great program. I recommend it. Please get in touch with me. If you don't have that email, I'll make sure it gets resent to you. Now, here in GraphPad Prism, I already have some data loaded up at a 0 and 5 million count time point. Had I wanted to add a new data set, I probably would have gotten a dialog box that looks like this. I would have chosen column, and I can choose, yeah, hey, I'm going to enter my replicate values, my pair repeat measures, and I'll go over some of these options as well. But here I have it set up already. And what's kind of cool is that as soon as I do that, it automatically generates a graph for me where I have these set up. I already spent a little time formatting. I can change some of the output or what type of graph this is. Here I have the individual values plotted. Uh, I could also do um, different box and violin plots. Box plots are sort of a nice statistical tool to show you the median, the inner quartile, the first quartile, the third quartile. That's the edges of the box, and then different interpretations on how to interpret what are called the whiskers of the box plots and Tukey minimum maximums, the 10th and 90th percentile are all different options. I won't go over what those individually mean, but those are there for you. Uh, you can also do column charts if you want to show the mean and median plus some sort of error bars, whether the standard deviation, the standard error of the mean, some sort of confidence interval. I think there's a growing trend towards showing the individual data, which I kind of like. It's a nice way of visualizing all the different data points and not hiding any potential outliers within averages and standard deviations. So here, the reader can see everything that they'd like. And then, so going back to my results, I can click this Analyze button and I get a nice variety of different tests to do. Here, I might want to choose to do t-tests. And here's where I can select, hey, are these unpaired or paired? Visually, I can get a nice sort of analysis of what they actually mean. So even if you forget that definition, here, unpaired, you can see they're trying to sort of indicate, hey, I'm going to average this whole group in column A and compare it with this entire average in column B. For paired, I'm going to go across the rows. Sample one, here, I'm clearly going to compare with the treated one in row one and use those. And here's where I can select a number of different options that I want, whether I want it to be one-tailed or two-tailed. Usually it's two-tailed unless you have a very specific requirement. Hey, I want to show that these are greater than 0.3, whatever the output is. I want to show that these samples are no less than 0.2 or so on. So two-tailed simply just means, hey, it's going to be significantly different if one's higher or lower than the other, but I'm not going to specify which one has to be higher or lower. And you can even input different options here. Do I want to just show the differences, or do I want to show the absolute values and just indicate their differences? So now I can go to my analysis for the paired t-test. You see, I got a great p-value here. It's nice and low, 3 asterisks. That's something you always want to see. If I wanted, I could always just pick in this box and pick different conditions. Maybe I do want a one-tailed. I want to change the pairing to unpaired, so I can always change these values around. And then I can actually even add those pairwise tests graphically, something in here, which is something that Excel unfortunately kind of lacks in this sort of formatting test. And I can format those to show the p-value if I want and apply that, have that put out, or I want those asterisks. You can change the definition of those asterisks and how to interpret those. And then even change the formatting of your actual pairwise testing, maybe make the line thicker or whatnot. Now, it actually might not be too common that you do certain t-tests. I'll get into that later, but for the most part, particularly the tests and the fatigue test that I have up on the screen, you're going to be perhaps a bit more interested in when you have more data sets beyond just two. So here, a very common statistical question is going to be, is there any difference among the groups, not just between the two, but now you have more than one? Is there any difference among the groups? So here, it would not be appropriate to use t-tests. What a t-test essentially do is ignore the data sets in the middle and eventually just sort of assumes that you've done no other tests besides those two. So it's inappropriate to use t-tests. What you want to do is a proper multiple comparison test that considers all the variance holistically across all your data sets and then does the appropriate comparisons. So again, you want to consider the total variance, which increases your statistical power, even if you want to look at only two groups and a post hoc analysis. So each comparison you do, and this is a few notes on this, each comparison you do does technically dilute the power of each test. I think the way it was explained to me is that every multiple group comparison test you do is essentially like buying another lottery ticket. Where if you imagine a situation where there truly is no differences in any of these tests, even though this one I'm showing you looks like it's trending upwards, if there's no difference in any of these values and you did 1,000 or 1,000,000 of these, it's very conceivable that one sample is going to have, because there's a variance within all these groups, some samples are going to be on the lower end and some samples are going to be on the higher end. If you happen to test randomly two groups where one were all at the higher end and the other were at the lower end, you're going to find some statistical comparison. So usually these types of tests somehow understand how many comparisons are being done and correct and account for that in your statistical power. So different tests incorporate different amounts of corrections for those multiple comparisons, and I'll give some guidance and how to lean on certain statistical programs to help you understand what to do. So in order to go back to that question, is there any difference among the groups? It'd be more appropriate to do an ANOVA test, which first really answers the question, is there any difference among the groups? Okay. And it's the first step in understanding whenever you have means of 3 or more groups to see if at least one is significantly different. Now, the power of this is that ANOVA looks at the variance within all groups, meaning, hey, whenever you don't change anything, so ignoring the left to right, but whenever I look at an individual group, let me understand the variance that's within each one. So it's almost like increasing your noise sampling to a higher degree and having a higher sample size and noise so that whenever you start making inferences across the groups, you have a greater statistical power in doing that comparison. So you want to use an ANOVA when you have at least 3 or more groups. You want to test if any of the group means are in general different. The data is continuous, meaning not discrete and is normally distributed. And the variances are roughly equal across the groups. So in this case, you can assume, even if you technically look at a standard deviation or variance within each group, you're going to find that they're different. What this is saying is that, hey, if the assumed total population across all groups have equal variances, and obviously you're only testing 3 or 6 or 12 within a certain test group, if you could assume that there's like 1,000,000,000 or 1,000,000,000,000 of them, can we assume that the variances are equal? And so for the purposes of these tests, yes, you can assume that. So now the next step, let's say you've run your ANOVA, but you still want to ask, are any of the groups different from one another? Okay. Now there's certain ways of interpreting that. Okay. Here's where you can still use the power of an ANOVA and the variance within all the groups. And you could potentially understand, hey, are any of the groups different from my baseline? Okay. Meaning you might only test with respect to the 0, but you're not going to compare the 2 million count with the 3 millionth count or vice versa. Now, this is where you might choose a statistical test like the Dunnett's test, which specifically limits the amount of multiple comparison correction, which in turn increases your statistical power. The other option is, let's say you don't care about just the baseline. You want to answer, hey, broadly, are any of the two groups different from one another? And that's where you basically take a little bit more diluted version, a Tukey test, that looks at all possible comparisons. Now, that means essentially buying more lottery tickets for that analogy I gave earlier. So it does has less statistical power, but it's a valid statistical test. And when you want to compare things or understand things simply beyond the baseline, this can in turn be very important and something that's powerful to do. Now, another option could be is if you want to understand how to compare your results with a constant or a specific value, meaning you might have a certain product specification. Hey, the femoral neck needs to have a modulus greater than 125 gigapascals. The femoral stem's deformation can't exceed 3 millimeters. Hey, I'm doing an osseointegration pullout strength test, and the strength of that integration and the maximum pullout strength needs to be greater than 1200 newtons. Those are all not comparisons of two different groups, but comparison of one group to a specified value. Now, here's where we're actually going to go back to our best friend, the t-test, because an ANOVA can't estimate a variance around a constant. That's nonsensical. So in a sense, what you're going to do are standalone t-tests where at each group, you're going to compare those to a specific number. Okay? So in this case, you have a few different options on how you want to do this. It kind of depends on the wording, how I displayed it, right? It must a modulus must be 125 gigapascals. That's where it's actually a two-way test, right? Your test would fail if it's either stronger or weaker than 125 gigapascals. So you really just want to see, is it different than a specification? And that's the default value in most tests. Most tests by default are two-way tests unless you're smart enough to specify. A one-way test is different. That's where you want to see if a value is either specifically greater or less. And it's not both. Both would be different. But if it's either greater or less than a specification, you need to pick which direction you want, meaning you got to pick either greater or less. Hey, the stem deformation can't exceed 3 millimeters. That means it needs to be less than 3 millimeters. The pullout strength has to be greater. It has to be greater than 1200 newtons. Those are two different one-way tests, both that go in different directions. One has to be less than, one has to be greater. Now, most programs by default offer two-way. In fact, GraphPad Prism, which I'll bring up a few examples in how I might do these tests, only allow for two-way. So the workaround, you have two options. You can either do a two-way analysis and then have your p-values, meaning cut them in half, or you can double the significance. So by default, usually your alpha, your significance value is 0.05 or 5%. But you might say, hey, I'm going to trick this program into doing a one-way. So therefore, I'm going to make it do a two-way significance test, but I'm going to set my significance to 10% as opposed to 5, because a 10% two-way equals a 5% one-way. So let me show you some examples on how that was done. Now, going back to GraphPad, here I have a column data table set up. And again, if you want to do this, I would, instead of going into, I'm actually doing the same type of column analysis that I did before. This time I've entered 5 data sets as opposed to just the single 2. If I go up to my analysis, I can pick a one-way ANOVA instead of doing my t-test. And then here's where I can pick my options. Again, am I doing a matched or paired data set, or am I not going to have any matching? So this would assume independent data sets between my million cycle counts. That's not the case. Each femoral stem is being tested at baseline, 1 million, 2 million, and so on. And I continue with that. Under multiple comparisons, this is where I could select some of my options. I might not want any. I might want to choose to compare the means of every column with the mean of every other column, in which case my options, I love how Prism does this. They even recommend Tukey. Again, this is the more slightly diluted variant. If I wanted to compare with a control column, and even if I didn't have them ordered in the right way, I could select which one is my true control. Then under options, it would recommend that Donut test. And if I wanted, I could pick others. I sometimes see Bonferroni. I'm not a statistical person. I don't know quite the differences between those, but I like how GraphPad will recommend these. And then you can even click this Learn button, go to the GraphPad website, and they give you some insights on the settings and some recommendations and whatnot. So I can press OK. Again, I can also go back and change some of the parameters of what I wanted, if I want to get every means or if I do want to compare it to a control option. This is the result of my ANOVA. It tells you first, hey, there is significance. There's differences somewhere, but I don't know where it is. So now I need to go under the multiple comparisons and understand, Okay, is 0 different from 1,000,000? Yes, it is. 0 different from 2? Yes, it is. And gets more and more significant from there. And again, if I go into my my column analysis, and I want to add some of those differences, then I could pick that and then say, yeah, let me put on some of these different comparisons and it'll show and automatically plot by significance here. I could go back in, I could reformat those. Now, I could also go and do what I mentioned before, a one sample t-test on any one of these. And I've already done this before, so this actually pops up. I'm actually just going to change the parameters. So it's going to edit my one sample t-test over here. So do I want to do a one sample t-test around the mean or do an alternative around the median? I'm not going to give the differences between those two for now. I recommend just doing the mean. And this is where you might say, hey, test it against a specified value. And let's say I put in a value of this is actually the mean of the very first group. Is any test different from, let's say, statistically different from that one or from that one value that's based on my baseline? I could put in a fictitious number, 0.4. Are there any options that I want to choose here? Again, if I want a one tail, I can change my significance and say, hey, yeah, it's got to be greater than that. Um, this will actually show me both differences before and after, and I might have to actually look to see if any of the samples are below and exclude those from my analysis. But for now, I could game it like that and then press OK. And now I can see those differences and see, yeah, here's the actual mean. In fact, I even forgot what value I picked, and it was 0.4. So this one is significantly looks like less than 0.4, significantly less, significantly less. This one, even though it is less, it's not statistically different, right? Same thing here, even though it's less, this one's actually higher. It's not statistically different, and you have your p-values. So maybe you want to say, hey, yeah, these groups are no different, whereas these values are significantly less. Again, it's good practice to figure out which direction are you going for. Right now, I did a two-tailed test, and if my criteria is that it can't be uh, less than 0.4, then these would fail, whereas these would pass. If I want to do greater, like it can't be greater than 0.4, even though my statistical test showed here, hey, it is significantly different, I know, hey, I'm doing a one-way test. Ignore these. And in fact, these are no different either. Even though this one is technically the mean is above there, I was showing statistically, it's no greater than zero point 0.4 according to my interpretation of the one-way test. Now, that takes care of my column analyses. There are cases where I might want to do group analyses, meaning that there might be individual groups or cohorts within each treatment cycle that I want to somehow separate and understand differences of. So that might be the case where I have, for instance, I've broken up my N of 6 into two separate N of 3s at each cycle count. So this could be any scenario where I have both placebo and control groups that I'm analyzing over time. Maybe I want to split up the demographics into by sex, male versus female, or race, to understand is my treatment affecting these two somehow differently? Or maybe I have two different batches of femoral stems, and I want to keep those separate within my analysis. Still do the same test that I talked about before, but include this as a unique factor that I also want to do statistical tests around. So in this case, instead of doing a one-way test, which in our case only looked at the cycle count, I'm going to separate some of those factors and do a two-way ANOVA, where I'm effectively adding another factor to do my statistical testing around. So a two-way analysis of variance examine those effects of two independent variables, which we call factored, on a continuous outcome to see if there's any difference or interactions between those. So do this whenever you have two factors. It could be time and treatment, time and batches, uh, demographics in time, like any of the examples I provided before. Each factor has two or more levels, right? I have two different uh, sexes. I have 3 different time points and so on. They're all in a quantitative outcome, or you're measuring a quantitative outcome, right? So obviously race or sex isn't on a quantitative, or maybe it is on a spectrum, depending on how you want to interpret that. Um, but treatment, placebo control are in 2 binary groups. It's the outcome, right? Whatever deformation, absorbance value might be testing that could be on a measured continuous outcome variable. And you want to know, hey, does factor A affect the outcome? Does factor B affect the outcome? Or is there a synergistic effect? Does the combination of A and B matters? Is some interaction between the two that somehow confounds the results as opposed to looking at each one individually? So I'll go back into GraphPad and show how we're doing this. So now, instead of having my original data just in a simple column analysis, I'll go to what's called a group data table, which you might have seen in the table format, not that, where if I clicked on new data table, I go to a group and you can kind of see here how it's going to be pictured. Yeah, right. At every treatment group, I want to somehow look at the differences between, hey, if this is 0 million counts, 1 million count, 2 million counts, I'm going to look at batch one versus batch two, or gender one versus gender two, and so on, instead of just doing a straight up and down control analysis. So now I've lumped it into a group analysis. And now I can say, great, there's 3 replicas, n of 3 at each time point across the 2 different batches or sets that I have. And now they kind of go down in order of how many different sort of macro columns that I want. So that's eventually going to look up or look something like this, where I have those split up. And now I can do certain analyses of these. So if I go back to my group analysis, I press analysis, say, and because I'm in a group data set, it automatically comes up with group analyses. And you can see here, you can even get into 3-way ANOVAs and some pretty complex tests. So I'm going to say, okay, I'm going to change the parameters of something that I've already done before. So again, first of all, am I doing, I want to say which ones are paired, which ones are matched. So you can kind of see which interaction I might go for here. Right now, I don't have any matching. Each column represents a different time point. And that's not the case. I had the different macro columns as different batches. So I might do something like this where, hey, these ones are matched and these are on different time points. So that's exactly the scenario that I have here. They don't go laterally, they go down. You could have done it the other way as well. You can name these. Hey, the batch that defines the column would be my batches. Group A is batch one, group B is batch two. That defines the rows would be the cycle count or cycles. And then whatever is matched within a subcolumn, Y2 is a unique sample that I have, or maybe it's a person, or whatever it is that you're taking these repeat measures on. Now, multiple comparisons, now you have a lot more kind of crisscrossing or mashing that you might want to do. Do you only care about matches across the 2 different subgroups, batch A and batch two, or batch B, group A or group B? Um, do I want to compare the broad mean? So here it's almost as if I'm keeping the data separate, but I'm going back to almost that one-way ANOVA analysis. I'm going to lump them together and just only compare mean by mean by mean. And that's the case where you could still select baseline as your control and kind of do that Dunn's test. Let's see. And in fact, here they even recommend Dunnit, but it wasn't automatically tested for me. I could compare within each column, compare multiple rows. So I'm kind of ignoring the batch to effect. I just want to know how does the individual means compare. And again, do I want to compare every mean or do I just want to compare to the single row? And then I can get more complex, or sorry, this is the other option. Don't compare across time, only compare across batches. Or, hey, let's test sort of every which way combination. In which case, do I want to compare both the batches Do I want to, let's see, compare within rows and all within columns, more conservative? You can do all different kind of combinations here. So you have multiple different ones, and each one's going to kind of recommend different types. Now we're back to the Tukey, Bonferroni, SIDAC comparisons I sometimes see in journal papers. So lead on these recommendations, understand which ones might be most appropriate to however answers your statistical tests. So I forget at this point what I selected. Um, yeah, let me kind of pick. Um, I forget why is it not allowing me to pick some of these other ones now. Um, no comparisons. Okay, now I'm going back to opening up some of these options. So now I could do something like this. Um, or go back and then let's see, one family, all comparisons. Let's just kind of do the recommended one. I could press OK. I could look at my options, click the recommended one, Tukey. I could pick my alpha values, my residuals. I'm not going to select any of these. I can press OK and then see whatever it outputs. So somehow it says, hey, the differences across batches was no difference, but cycle did absolutely have an effect. So again, just like with a one-way ANOVA, I know now there is a different. As far as what's different, I need to look at my multiple comparisons tab to see which one. So just comparing at each cycle count, group A to B, this is that batch to batch test. I do see one unique individual answer. It's kind of interesting that the ANOVA said, hey, the batch representation doesn't make a big deal, maybe because there's so little difference in some of these other ones. But I just had a weird result here. I could probably justify that easily, despite the fact that there was a difference at 3 million cycles. If I truly want to conclude that there was no difference, I can lean on the statistical powers of these other groups and maybe the overall ANOVA. It's kind of interesting. I'm a little bit curious at how you could have an individual result, even though the bulk ANOVA said there was no difference. And then here's the individuals at group A, which ones are different from one another. Again, I did the Tukey, so the most liberal and the most dilute of all tests. And then if I were to go down to my group analysis, right now I started plotting every significance that I've found. That might be too much. Again, you might want to lean on whatever hypothesis test you had. Was it truly you need to find any difference that was there? Or is it you want to see if there's any difference from the baseline? If so, get rid of some of these comparisons. But that kind of gives you some insights on how to use GraphPad Prism to not only do these statistical tests, but to show you some of these differences. So now lastly, I'll kind of close out just by going over some general tips on maybe how you should report some of these. Uh, you very often might have to do a two-way ANOVA to see what large differences there are against complex groups with multiple sub-batches. If you fail to see any significance, let's say between batches, you can rerun the results as a one-way ANOVA as long as you report some of those transparently. So I even gave some sample verbiage here. Hey, two-way ANOVA is first conducted to assess the effects of treatment and time on whatever outcome. The interaction between treatment and time was not significant, and treatment had no main effect. Therefore, data was collapsed across treatments, and a one-way ANOVA was performed on time alone. That's perfectly acceptable. That might make some of your graphical representations a little easier, as opposed to having to report tons of tables with all the unique different p-values across these multiple subgroups. So that's absolutely permissible. Going back to the acceptance criteria in your reports, you always want to analyze your quantitative acceptance criteria, meaning ones that have to do with either differences between batches, differences from one another, or to a certain specification that you have, with the proper statistical test. So in cases, even when all of your individual samples meet a certain criteria, like, hey, none of the deformations exceeded 3 millimeters, you might still want to run a statistical test to show that, hey, our small sampling of our, N of 3 or N of 6 total samples statistically gives us confidence that not only did these samples not exceed 3 millimeters of deformation, but the entire assumed population, to a high degree of confidence, would not have exceeded these as I continue testing to a higher sampling degree. So use these to your advantage, even when your individual tested samples meet a certain product specification. You always want to specify the statistical test and the conditions in which you ran them in your test reporting, some sort of data analysis section. Historically, for me, it's always been the very last section of your materials and methods, your procedures section, usually right after acceptance criteria. That way, you have your acceptance criteria kind of stated in broad terms or to unique specifications. And then your data analysis explains, hey, for the deformation test, we did a one sample t-test to understand if deformation exceeded 3 millimeters. We did a two-way ANOVA with a Dunn's post hoc test to understand XYZ, and so on. And then lastly, you should always, your significance and p-value should always reported after having performed certain statistical tests. So you might have tables that summarize these graphically. As I showed you in GraphPad, you can put those asterisks or the actual p-values within your actual graphs as well. And always frame these in reference to your acceptance criteria. So you don't need all of those p-values, exhaustively in tables if they don't really speak towards your particular acceptance criteria or your statistical test. So keep these simple, make sure they conform to your acceptance criteria, cut out unnecessary tests, and only use the data that you report as a way of, in a sense, arming your arguments with ammunition, statistical ammunition, to show that you met these acceptance criteria. And that's it. Hopefully this was helpful. Again, if you need to download that GraphPad Prism program, I provided our entire class with a license. You should have got an email early in the semester. If you didn't, contact me. I'd be happy to resend that email.